Assalamu alaikum wa rahmatullahi wa barakatuh. This is the second presentation on analysis of frames. So today I'll have two examples. This is the first one. You could see the structure shown. If we want to calculate the reactions for this structure, we'll simply do sigma ma equals 0. So this is the 12 times 5 plus 24 times 3 plus 6, which is the distributed load, times 6, which is the distance, times another 6, which is 3 plus 3, which is the distance, plus 15 times 2.5 minus 9 VF. So this will give us that VF is equal to 42.83. So sigma Fy equal 42.83 plus VA minus 24 minus 6 times 6. So VA is 17.17 kilonewton up. Sigma M down equals 0 equal 15 times 2.5 plus 5 times HF. So HF equals 7.5 kilonewton to the left. Sigma Fx equals 0, so 12 plus 15 minus 7.5 plus HA, so HA is equal to 19.5 kilonewton to the left. So if we look at each of the members on its own and take a section at each joint, we will see the following. If we look at member AB, we will and look down, we will find the axial force, the 17.17 kilonewton. So this is in compression. There's nothing else causing compression or tension other than this force. Then there is the horizontal reaction, the 19.5 kilonewton, and there is no horizontal force in between. So it is the same all over the section, all over the member AB. And of course, at hinge A, there is no moment because it's a hinge. However, if I take a section at B, if I look at moment, the moment will be the 19.5 times 5, which is 97.5 kilonewton meter. If you look at member BD, again, due to joint equilibrium, we must see the same 97.5 kilonewton meter. At D is an intermediate hinge, so the moment must be 0 over there. Then we look at the axial force within the member is the 7.5 that was transferred from joint D, and we'll see where is it. So if we take a section anywhere between B and D, we will see the horizontal reaction HV, or we will see the other horizontal reaction HA, which is 19.5 minus 12, so this is 7.5. So you should reach the same result, which is a 7.5 kilonewton in tension. Then if you take a section just beside B, we will see a 97.5 kilonewton meter bending that we talked about, and we will see the 17.17 kilonewton coming from the reaction, the vertical reaction. If we take a side just before D, we will see the 42.83 kilonewton, which is the vertical reaction at F. We will see it as a shear force at D. If we look at DF, the member DF, and we look at joint D, we will see the axial force. This is the 42.83 kilonewton. This is the reaction. It's called a compression. And we will see at joint D, we will see a 7.5 kilonewton as a section, which is simply the reaction, the 7.5, minus the horizontal force, which is 15. So this will give us another 7.5 kilonewton. So if we draw the axial force diagram, we'll see the 17.17 force of compression in AB, a tension of 7.5 kilonewton in BD, and a compression of 42.83 kilonewton in DF. Meanwhile, if we look at the shear force diagram, we will see a constant shear force at AB of 19.5 kilonewton, which is the horizontal reaction, and a constant shear force between B and C, which is the 17.17 kilonewton, which is again the vertical reaction, and then a sudden drop from 17.17 to 6.83. This is due to the concentrated force of 24 kilonewton. Then we will see a gradual change in force from negative 6.83 kilonewton to negative 42.83 kilonewton Now this is due to the distributed load. So if we take a section, so the difference actually between 6.83 and 42.83, this is the 36 kilonewton, which is 6 times 6. If we take a section just beneath D, we will see 7.5 minus 15, so this will give us negative 7.5 kilonewton. Then just at the location of point E, a sudden change happened, which is the presence of the concentrated load. So this, instead of having a minus 7.5, so now it's minus 7.5 plus 15, so it is plus 7.5 kilonewton. Then at joint F, it should close again to be 0. So it will be dropped from 7.5 to have a 0. So the shear force should close. Then if we look at the bending moment diagram from the shear force diagram, we notice that the only point of crossing between positive and negative shear is joint C, is point C. So point C is the location of the maximum bending moment. This is a fact that we know. And another 3 facts that we know is that the moment at A is 0, moment at F is 0, moment at D is 0. This is because the A and F are hinge supports and D is an intermediate hinge. So it must be like that. Okay? So if we take a section just beneath B, as mentioned before, we will see a 97.5 kilonewton meter, which is the 5 times 19.5. And due to joint equilibrium, we should see it from one side the same like the other side. So it is the same positive 97.5 kilonewton meter. If we take a section at C, we will see the maximum force. You could look left or look right. This will not make any difference. If you look left, you will see 17.17 times the distance within the same direction plus 19.5 times 5. 17.17 is multiplied by 3, then 19.5 multiplied by 5, and that's it. So this should give me the value of the 149 kilonewton meter. So if we take a section at E, we will see an 18.75 kilonewton meter, which came from simply a 7.5 multiplied by 2.5. So this will give us 18.75 kilonewton meter. The other example here, you could see you have a cantilever connected with an intermediate hinge to a frame. So if we substructure this nice structure, we will see the following. We will see that sigma moment about B will give us 0 because B is an intermediate hinge. So 38.7 times 20 minus 30 times 9. What's the 30? The 30 is 5 times 6. What's the 9? The 9 is 6 plus 3. So this is the location of the resultant of the force, the distributed force. All that is minus EY times 12. So this will give us EY is equal to 42 kips. Then we'll go and calculate sigma Fx and sigma Fy. Sigma Fx equals 0, so the force that we'll call Bx, which is the force transferred from that part of the structure to the other part of the structure, this is simply equal to, so this is simply negative Bx plus 30 equals 0, so Bx equals 30 kips. Sigma Fy equals 0, so negative By plus 42 minus 38.7 equals 0, so By is 33.3 kips. So going back to the other part of the structure, we will put the Bx and By that we have calculated, we will reverse the sign and put them as loads. So now this will give us that Ay is simply equal to the same value of By because there is no other force. So, but it's opposite in direction. So sigma Fy will give us that Ay equals 3.3 kips. Sigma Fx will give us that Ax equals 30 kips. If we take sigma moment about A, we'll find that MA, the moment reaction, is 39.6 kip. feet. So this will tell us that the axial force within this part of the structure, within part AB, is 30 kips. This is tension. Then the shear force is simply minus 3.3 kips, because if I take a section anywhere between A and B, I will see the same negative 3.3 kips in shear force. Meanwhile, the moment at B must be zero, because B is an intermediate hinge. And if we take a section at A and look at the moment, this is equal exactly to the moment reaction, which is 39.6 kip feet. And again, we draw the positive side down, because we always draw towards the sign of the curvature, towards the side of the curvature. Meanwhile, if we look at the other members, if we look at member CE, so if I take any section between C and E, I'll see the axial force is negative 42 kips, which is the reaction. If I take a section anyway, if I take a section just above E, I will see zero shear force, because this is a roller support. However, the shear force will keep on increasing until reaching 30 kips at the end of the distributed load, which is equal to 30 kips, the resultant of the distributed load. And as there is no load between the last point in the load and joint C, as there is no load there, the shear force will be constant. It's stagnant. It's not changing. It's remaining as 30 kips. So when we draw the bending moment, we know for sure that E, because it's a roller, it's a zero. So the highest moment, simply you will take a section just beneath C, and you will see the 270. From where did the 270 come? It simply came from the 30 times 9. So 30 times 9 is 270 kip feet. Then if we take a section, if we look at member BCD, we will see that if I take a section between B and C, I will always see the tension force, the 30 kips. However, if I take a section between C and D and look right, I will see nothing. So the axial force between C and D is zero. Then if we look at shear, if we take a section between B and C, we will see the force By, which is negative 3.3 kips. But between C and D, what happened new is that Ey came into the equation. So now I could see Ey minus 3.3. So this would be plus 38.7 kips, which is the same 38.7 kips, the load at the end. So that means that we are doing a good job. Everything is correct. When it comes to the moments, I must take a section before the column and after the column. If I take a section before C, I will see 3.3, negative 3.3 times 12. So this is negative 39.6. If I take a section after C, I will see negative 309.6, which is simply negative 38.7 times 8. So this is negative 309.6. So what's that difference? The difference between 309.6 and 39.6? This is exactly 270. So this is what we call joint equilibrium. That the difference between the 309.6 and the 39.6 should come from the 270, that is the moment applied at the column CE. So this is the concept of joint equilibrium that must be satisfied, and you must understand that very important concept.